Welcome back to Calculus 2, Section 2.5, Physical Applications. We have a number of different applications to go over in this video. We're going to start with mass and density, and we'll look at two particular types of density, linear density and circular density. Let's start off with mass. So imagine that you have in front of you a thin rod. This looks pretty thick to be called a thin rod. Let's slim it down. And if it is indeed a thin rod, we can model it as an interval on the number line. And it becomes a one-dimensional object. So here's a closed interval, a to b, and we're letting it represent a thin rod. Now, if we pick any point of the rod, we're picking an x value between a and b, and we want to let rho of x be a function such that it provides us with the density of the rod at x. Good. Now assume that rho of x produces a value which is constant, irregardless of x. Then we can find that the mass of the entire rod would be the density, rho, which is constant, times the length. So what we want to consider is, what if rho is a variable density function? If we were to choose a different location for x, it would produce a different output. That's a variable density. And what we're going to do is we're going to show that under that situation, we can recover mass as an integral of the density function. And what's key is for us to appreciate that in the simple case where rho is a constant, at every point the density of the rod is the same, that the mass can be recovered by taking that constant times the length of the rod. Okay. So now we're assuming that rho is not constant but is a variable density function. And our objective is to recover mass as an integral of rho. If we're looking to recover an integral, we should do the normal trick, create a regular partition. Good. Then look at a representative interval, the ith interval. Take the partition fine enough, take n sufficiently large, such that if we pick any point in the representative ith interval, that the values of the density function are all nearly the value at one single point. In other words, that the density function over this interval is constant, essentially. So we can always be assured to have n large enough. We can always find an n large enough such that this will hold. That's assuming that the density function is a nice function, continuous function. Well, if n is taken large enough, over this interval the density is essentially constant, then we can find the mass of the thin rod over that subinterval simply by taking this constant times the length of the interval. Oh, well, we do that for each of the subintervals, add them together, and then we have a nice approximation of the mass of the rod. Sounds good. And then looking, we have a sum of a function evaluated at arbitrary points times the length of each interval, we're looking at a Riemann sum. And whenever we form up a Riemann sum, we can limit the Riemann sum to produce a definite integral. Excellent. So what have we recovered? We've recovered mass written out as a definite integral with integrand, the density function. Do a quick check. What if the density function was a constant? Would you recover that constant times b minus a? Yeah. Very nice. So here's a formal statement of what we've just gone over. Given a thin rod oriented along the x-axis over an interval, a to b, with linear density, rho of x, then the mass of the rod is given by mass equal to definite integral, bounds of integration, a to b, integrand rho of x. Very nice. So we've shown how, provided a density function, we can recover the mass of that object. And the example that we've looked at is using a linear density function. So in this case, where the thin rod is represented by an interval, a to b, on the real number line, then changing the point of the rod that you pick would change the density function. Changing the linear location, then this is a linear density function. Okay, so that's some vocabulary. Next, let's consider the idea of a circular density function. And instead of the object being a thin rod, let's suppose that we want to consider an object which is a thin disk. The thin rod is a one-dimensional object, or rather modeled as a one-dimensional object. And the thin disk can be modeled as a two-dimensional object. Good. So let's look at the disk. If we have a disk, the disk has a measurement called the radius. So let the radius be little r. And then let's think about this disk, the density, the mass density of this disk. So if we were to pick any location of the disk, we would want a function to provide the density at that location. When does that density function become a radial density? The situation is that if we pick a point, look at the distance to the center, call that x as the distance, and then think of all other points in the disk which are exactly this distance x from the center. Rho is a radial density if all of the points along this circle of radius x have the same density. Now, if you vary the radius to some other value, x, and it's still the case that all points of this radius x have the same density, then this is a radial density function. Beautiful. So now we know what a radial density function is. Let's think of the integral that will recover the mass of an object which has a radial density function. Good. So because every point has density provided simply by the radius, we should be able to recover mass simply by integrating with respect to the single variable, providing the radius. We want to recover an integral, thus we're going to partition the interval from 0 radius out to the radius r of the disk. Good. Let's look at a representative point. Let's start the representative interval at x sub I minus 1. Consider the area of the disk with radius x sub I minus 1. And that radius is pi r squared, or pi x sub I minus 1 squared. I'll term this the small area. And this is using the left endpoint of a representative ith subinterval. Let's now bump over to the right endpoint of the ith subinterval, x sub I, and consider the area of the disk that it determines. That area would be the large area, pi xi squared. Good. Do a simple calculation of big minus small. That leaves us with this shaded ring. Technical term for this shaded ring is an annulus. This annulus has area a sub I, given by the difference of the big area minus the small area. Let's do a little algebra. Well, we have a pi that can be factored off of each term. Doing so leaves us with a binomial, which is a difference of squares. We know how to factor a difference of squares. Just like in the previous video, we can take the difference and we can reterm that, the length of the subinterval, delta x. And on the binomial, which is a sum, divide it by 2, and then multiply by 2 to cancel out. So multiply by 2, divide by 2. And then this quantity is the average value of the left and right endpoints. It's the midpoint. And then write this out. So 2 pi average value of left endpoint and right endpoint, or the average radius. And then remember that 2 pi r, that would be the formula for the circumference. So we're taking the circumference at the midpoint radius and then multiplying it by some small width, delta x. So what was AI? A sub I, the area of the annulus. Good. So this is for a representative ith subinterval. And then we can compute out a sub I. Compute out a sub I for each representative interval, and then add them together. And if you multiply each a sub I by rho at xi star, rho is representing the density. The density at each point in this annulus is going to be the same, approximately. Thus, this product is going to give you the mass of this annulus. Swap out for the formula on a sub I, and here's the expression for the mass of the ith annulus. And now, adding up all those mi's gives you an approximation to the mass of the entire disk. Recognize that we have a Riemann sum, which we can limit as the number of annuli goes out to infinity to exactly recover the mass of the disk. So note that the formula is involving the constant 2 pi as well as the radius x multiplying the density function. So this is a little bit different from the linear density function that we have to attach to each location on the interval 0 to r a circumference measurement. Good. So here's an assignment. 1, compute the mass using a linear density function, and then 2, compute the mass of an object which has a radial density function. Nice. So that's the first topic, mass and density. The second topic is work. And we're going to begin just like we did in mass and density. For mass and density, we began by first considering a constant density. We took that constant density and multiplied by the interval to come up with the mass. Same notion here. If we start with a constant force and we can multiply by the interval, we'll come up with a work quantity. Let's take a look. So this is constant force. And suppose that a body, an object, a mass, is sat nicely on the ground. That body has mass, and therefore here on Earth has a weight which we can measure in pounds. If we want to lift up the body, we have to overcome its weight. So we need an equal and opposite force applied to the body in order to lift it. Now, as we lift it, we can assume or make the assumption that the body doesn't change its mass, doesn't change its weight, so that if we lift the body a distance L, that we're at every single point along this interval of length L, we're having to apply a force F, constant F. Then the work done lifting the body at a distance L would be the constant force times the length L. So here we're assuming that the body doesn't change its mass, and therefore the force will remain constant. So applying that force over this distance, how much work is done? Think about it. If you have to lift further, it's going to be a harder effort than lifting just a tiny bit. Nice. So just like we saw in mass, we begin with the basic constant density here, constant force, and then we can switch over to variable density and create partitions over which the density was essentially constant. We're going to do the same thing here. Okay. So make sure that you're digesting well this notion of work. And let's press on. Nice. Let's talk about units for a second. There are two systems that we might encounter: US customer units versus SI units, International System of Units. Now, we looked at an example where the body has a weight, and the weight was measured in pounds. That's the force. We moved the body a distance. A measurement for distance is feet. Thus, the work units would be in foot-pounds. Very good. Let's look at the SI units. For force, the measurement is in newtons. Distance, a measurement, is in meters. And work is given in joules. Newton meters, joules. So depending on how the problem is set up, you'll either be using US customary or SI units. Good. So we've done the constant force. Let's look at an example of variable force. And this is going to introduce the notion of Hooke's law. The red box is representing a mass. The black line is a spring. On the right end of the spring, the mass is attached. On the left end of the spring is attached to the wall. This setup is known as a spring mass system. Currently, the location of the mass is at position 0. We'll call that equilibrium, meaning that if we introduce no external forces, the mass will continue to sit at this location as time goes on. Let's introduce a force to move the mass to the left. That would have the effect of compressing the spring. The behavior of the spring would be to push the mass in the opposite direction. The effect of that then is, as we start here at equilibrium, it will be easy to begin to compress the spring. But the more and more we compress the spring, the more and more the spring wants to push back. Thus, the harder and harder it becomes to compress the spring further. This notion plays out as we move to the right as well, that in the beginning it's easy to move the mass to the right, but the spring being stretched wants to compress and return the mass in the opposite direction. The point is that as we move more and more to the right, the more and more the spring wants to bring the mass back to the left, the harder it is to move the mass further to the right. So this is the notion of Hooke's law. Hooke's law is the statement that the force required to displace a mass from equilibrium is proportional to the distance of displacement. Good. So here, the location of the mass, let's say, is at -12, so that would be x. And x being a negative value means that the spring is compressing. If, on the other hand, the location of the mass was at a positive x, the spring would be stretching. And then the quantity k is a constant. That's a proportionality constant. So write this down. K is the spring constant. Think about if you have a spring as found in a mechanical pencil versus a spring found in the suspension of a vehicle, the spring constants are going to be different. So K is an intrinsic property of the spring. Good. And then X is the displacement from equilibrium. And recall that equilibrium is the state in which no external force is being applied. The mass would sit in its location unchanged. Good. So this is Hooke's law. Now, we have gone over work computed if the force is constant. We've looked at an example of variable force. Let's do generally how to compute work provided a variable force. All right, so here's another example of variable force. Consider the constant force example we had earlier. If we want to move the body from position A to position B, assuming that the body doesn't change in its mass, in its weight, then that would be a constant force. To make it a variable force, assume that the mass of the body, the weight of the body, changes as you move from A to B. Then the force required is going to be variable. Now what we want to do is determine how much work is required to move this mass, this body, from A to B. And what we can do is our typical, create a regular partition, consider how much work is done to move the body over a representative subinterval. So here the body's at the left endpoint. Move the body to the right endpoint. If we take that distance to be short enough, then we can assume that the body is not changing in its mass, and therefore over this subinterval we can assume that the force required is constant. Let Wi represent the work done over this subinterval. Then we can approximate Wi with the force at an arbitrary point in this subinterval times the distance. So in other words, constant force then times distance. Good. Change out the notation for the distance of the subinterval. And you guessed it, sum up all of the Wi's to get an approximation to the work required to move the body from the starting point to the ending point. Note that we have a Riemann sum, and we take a limit of that Riemann sum to come up with a definite integral for computing the work done by a variable force over an interval A to B. Very nice. Let's do an example. All right, so we're coming back to the Hooke's law situation. Let's read. Suppose it takes a force of 10 pounds to compress, take note of that, compress a spring 4 inches from equilibrium. All right, so we're compressing the spring. Therefore, the force that we want to apply will be towards the left. We'll take this value 10 and we'll change it into negative 10 as we want to compress the spring. As we're compressing the spring from equilibrium, the equilibrium point, take that to be at x equals 0. And then if we want to compress, we want to move to the left. So we want x to equal negative 4. Good. So under this setup, all we're going to do is find the spring constant k. So we apply Hooke's law, F equals k times x. We've set F equal to negative 10. As we're compressing the spring, we want to move to the left. And then for x, we've set x, well, x is given out as 4 inches. We would like to represent this 4 inches in feet, so we get 1/3. And then as we want to be to the left of equilibrium, we make that negative 1/3. Excellent. So the spring constant is k equal 30. Okay, Let's use this same setup and now ask a follow-up question. So in this setup with spring constant k equal 30, how much work is required to stretch the spring 6 inches? All right. So we set up our work integral. We know that the variable force is 30 times x, and that we're starting with the mass at equilibrium 0 and finishing with the mass at 6 inches to the right. We are stretching the spring. 6 inches in terms of feet is 1/2 foot. And then along the way, as the mass travels from equilibrium point to 6 inches, at every single point, the force required to continue to move the mass is 30 times its distance from equilibrium. So to add up all those forces is a continuous operation which requires computing an integral. We know how to evaluate an integral. Fundamental theorem of calculus, part 2. Bounds are nice, 1/2 and 0. Evaluate at the top and come up with your numerical value. As this is an application, let's recall the units. So we were given pounds for the force, inches, which we converted to feet for the distance, and thus the work unit is foot-pound. Beautiful. And a reminder that under SI units, force is newtons and work is Newton meter, otherwise joule, capital J. Okay. So your turn. And note that in this problem, the units are SI units. Very good. And that in this problem, the units are US customary units. All right. So that is work done by a force. We looked at both constant force, used that simple principle to expand to a variable force by creating partitions, Riemann sums, and taking limits. So work. Next, let's deal with fluids. We have 2 more applications. First one's going to be work done in pumping. Both of these applications are going to deal with liquids. So here a liquid is stored in a container. Let's call it a tank. This tank has an overall height of h, the tank itself. The tank itself is a cylinder with radius r. And then the liquid has depth d. We want to pump the water from the tank and empty the tank. Now, a convention that we will adopt is to measure into the tank from the top at depth 0 down to a depth of x. So x is a positive quantity. And despite being vertical, we're using x as the variable. Okay, so for this particular tank, let's assume that the height is 100 meters, that the depth of the liquid is 80 meters, meaning that the surface of the liquid occurs at a depth from the top of 20 meters, and that the bottom of the tank is 100 meters from the top. Very good. So, considering a representative depth of x at an ith subinterval, let's think about just removing all water at this depth by considering a representative slab of liquid. Okay, so this slab of liquid, how much is present? What is its volume? Well, we can compute the area of this disk, pi r squared, and then multiply by its depth, delta x. So we need to remove this much liquid, V sub I. How do we remove it? We have to pump it to the top. And pumping it to the top, we need to consider how much weight is present. The weight density of water, we can recall, is 9,800 newtons per cubic meter in SI units, or in US customary units, 62.4 pounds per cubic foot. All right, so keep those handy. Thus, we've figured out the volume present at a depth, and multiplying that volume by the weight density produces the force that this water has acting on it, which we must overcome. And then this volume of water is not going to change as we pump it to the top. So if we take this force and we multiply by the distance that it must travel, then that is going to give us the work required to remove water at this depth. We pump it to the top, then the work required. How far do we have to pump it? Remember, we are taking the top to be 0. We measure down to a depth of xi. We have to pump that to the top. Then that's how much force are we overcoming? We're overcoming 9,800 times the volume quantity multiplied by the distance. Then let that be represented, W sub I, as the work required to remove that volume of water at the depth xi. And then consider all representative depths xi and sum up their corresponding work quantities to approximate the total work required in pumping out the liquid from this tank. Very good. And we're looking at a Riemann sum. We know what to do with a Riemann sum. We take a limit. Pay attention to the fact that our bounds of integration are 20 to 100, as from a depth of 20 down to a depth of 100, there is water present. Good. 9,800 pi r squared, all of that is a constant. We can bring that to the front. And then all that we have is, for integrand, is the depth. Okay, so this is how we would compute out pumping a cylindrical tank. What if the tank were of a different shape? Suppose, like here, we have a cone. Let's find some measurements for this cone. Suppose that the height of the cone is 6 meters, and the circle at the top of the cone has radius 4 meters. Then we also need to specify the depth of the water. The overall depth would be 6, and then suppose that the depth of the surface of the liquid is 3 meters. All right, so that's the setup, and that's enough information for us to go and compute the work required to remove all the water from the cone. But what's going to be required is to come up with the volume of water present at some depth xi. So that you can see, as we were taking a larger and larger depth, the volume would become smaller and smaller. So we need to come up with an expression for the volume at an arbitrary depth. Okay, so our goal is going to be to try and simplify the picture and then argue off of the simplified picture. And what we can do is we can introduce triangles. So we have the large triangle for the cone. Then we have a smaller triangle representing a depth of xi. So for the larger triangle, the base will measure 4. And then for the smaller triangle, the base is going to measure ri. And then this is the information that we want to take away from our picture of the cone. We just want to work with these similar triangles. Let's continue to label. I'm going to redraw the triangles. So remember that the large triangle is going to have a height of 6, and that the smaller triangle results by reaching into the cone by a depth of xi. So we want to take away that xi from 6 to come up with the height of the smaller right triangle. Okay. And since we are interested in coming up with a expression for r in terms of x, we set up similar triangles, and then coming up with r as an expression of x, we'll be able to determine the area of this disk at depth xi. So here are the similar triangles being applied, and we want to solve for r. Good. So with this expression of r, we can compute the area of this disk and then multiply by delta x to get the volume. So area is pi r squared. We have the binomial squared. We have a pi. 4 over 6 is 2 over 3. Squaring 2 over 3 gives you 4 over 9. All right, so that's the area of one of the disks. And then you need to multiply that by delta x to come up with the volume of water at this arbitrary depth. Now, this is the measurement, the volume measurement of water present at this depth. We need to know the force that water has. So F sub I, take the volume and multiply it by 9,800. And then if we multiply this force by xi, then we can come up with the work required to lift that water from its original location to the top of the cone. Good. So a slab of water at a depth of xi requires this much work to lift it to the top of the cone. Add up all of these w sub i's to come up with the total work required to drain the tank of its water, pump the tank of its water. And then take a limit of that Riemann sum to get a definite integral. And then let's focus on, we have a constant, 39,200 pi over 9. And then for the we can bring that all to the front. And then for the integrand, we'll have an x multiplying binomial 6 minus x quantity squared. And then pay attention to the bounds of integration, that from the top of the cone, we reach down to a depth of 3 to find the surface of the water. That's where we have to begin pumping. And we continue pumping water until we get down to a depth of 6. Hence, bounds of integration, 3 to 6. All right, nice. So now we have a nice elementary integral that we can evaluate to come up with the work. And since we're using SI units, we write down our numerical value attached with the unit of joules. Very good. So here's an example for you to work on. Note that you have US customary units so that the water density will be a different numerical value. And in this case, in taking cross sections, instead of working with circular cross sections, you'll have square cross sections. Very nice. So that's work done in pumping. And next is hydrostatic force. Here's a picture taken by Ansel Adams in 1941 of the Hoover Dam. The Hoover Dam holds water as a reservoir, releases water to generate energy. Water is very important for our everyday lives, for agriculture. Having a dam hold the water, therefore, is a worthwhile endeavor. All right, so here let's look at a body of water, and this is looking at, think of it as a fish tank from the side. Let's drop into the tank a plate and let the plate fall to the bottom and sit flat on the bottom of the tank. Let the depth of the plate be at a depth of S. And then represent the area of the plate with capital A. And then sitting above the plate is a column of water. And then the volume of that water is A times S. Good. Then think back to when you're a kid, playing the game Dog Pile. You have your favorite friend, want to show them how much you appreciate them. And so everybody comes over and stacks themselves upon that person. That's essentially what's going on here. This column of water is sitting on the plate, and it's applying a force to the plate. So we know that the volume of the water is A times S. And then if we multiply by the density of water rho, then we get the force being applied to this plate. All right. The notion of pressure would be force per unit area. Right. Let's let lowercase p be pressure. Then the pressure applied to the plate is the total force, calculated here, divided by A. Notice in the force, A is present. Canceling that out, we can simplify that to the density times the depth. Good. Okay, so the English system, otherwise known as US customary, gives pressure in units PSI, pounds per squared inch. In the metric system, or the SI units, pressure is given in terms of pascals or newtons per squared meter. Good. Now, recall, Pascal's principle is the notion that the pressure at a given depth is the same in all directions. So this is in a fluid. If you were to think about that column of water taken away from the tank and just the column of water, that the instant that you let it go, it will, since pressure is given in all directions, the column of water will not maintain its form, but water will push away from the column and the column will collapse on itself. Pascal's principle is also what allows for a hydraulic lift. So this actuating this handle can lift a vehicle, for example. Okay, so let's do an example here. Let's go back to the Hoover Dam. Let's look at the face of the Hoover Dam. And let's represent the dam by this trapezoid with given measurements, 1,250 on the top, 750 on the base, and a depth of 750. Then, due to construction concerns, the dam will extend down into the earth, and a portion of the water interfacing with the dam is highlighted in blue. Good. So we want to determine how much pressure the water is exerting on the dam, and then from there be able to engineer a dam to withstand that pressure. So this is hydrostatic pressure. All right, so we have our setup. We want to know the water, how much pressure is it exerting? Good. So we're going to assume that from the top of the dam, the water sits at a depth of h below the top of the dam. We'll take that from the top of the dam, water exists all the way down to a depth of 540 feet. And then we're going to partition up this trapezoid into a square and two triangles. And then what we'll do is we will measure from the top of the dam down to a depth where there is water. So some arbitrary depth x. And then we will consider the width of the dam at that depth. And we have a strip highlighted in white. This strip is going to have a width of w of x. Okay. So we know that the width will at least be 750. And then we also have to add in the two portions given by the triangles. Introduce notation, let that be r. There are two copies. So w of x will be 750 plus 2r. Now our job is to come up with r expressed out as a function of x. And we're going to end up using similar triangles. Given that the top of the dam has a width of 1250, if we subtract the measurement of the side of the square, 750, divided 500 by 2 to get 250 for the base of these triangles. And we're interested in coming up with the measurement r. But r is the base of a similar right triangle. The height of the similar right triangle with base r is 750, the total measurement of the square, minus x, the depth that we drop down into the dam by. Good. So here are the similar triangles. And we're interested in an expression of r in terms of x. So using similar triangles, we come up with r as 250 minus x over 3. Good. We can plug that in. And then come up with w of x as 1250 minus 2/3 x. So that's the width of this strip at a depth of x. Now we want to consider the area of this strip, and then the area of this strip, w of x times delta x, is the amount of area, approximately, of water at this depth interfacing with the dam. Remember that pressure was force per area, so now we have an area measurement. W of x times delta x. And then we can look at the force exerted on this strip. The force would be the weight density, so that's of the water, times the area, and then times the depth. Good, so let's bring all those in. So the weight density is rho, that's for weight density of water. The depth will be x, and then the area is w of x delta x. So this is the force at a depth x, but really think that's the depth of at xi. And then if we find n strips at depths xi, add up all those forces, then we can come up with an approximation to the total force exerted by the water on the dam. Then we have a Riemann sum, which will allow us to take a limit and then find that the force exerted by the water on the dam is given by this definite integral. Beautiful. Now, here is an example for you to work on. We have a body of water. We're going to submerge a plate vertically so that the top of the plate is 10 feet from the top of the water. And you want to consider, just like we did on the dam, vertical strips. And you can see that as you look further and further, deeper and deeper down into the water, the horizontal strips have varying widths. Very good. That brings us to the end of section 2.5, physical applications. Thank you so much for watching. Please like if you find the material useful. And see you on the next one.